The Verilog module containing the code used to perform the testing is known as the test bench module. A Verilog test bench module is required to specify testing details. This module is unique in that it has no input or output ports. In other words, there are no connections that can be made to this module. Inside the test bench, the data to test the module is defined or obtained, and the design module to be tested is specified. We can view the module relationship between the test bench and the design module as part of a hierarchical structure, and it can look like this. At the top of the hierarchical structure we have the test bench module, which relies on modules beneath it, that is the design module that is to be tested. One approach in practice is to have a unique file for each module. Part A shows the hierarchical relationship between the modules. In this case we have 4 unique modules: the test bench module, the top level design module, the processor module, and the UART module. And on the right hand side in part B we note that we have 4 separate files. The logger.test.v file contains the test bench. The logger.v file contains the top level design module, and then we have 2 further files, the processor.v file and the uart.v file, containing the processor code and the UART code respectively. The design undergoing testing is often referred to as the device under test, or DUT. So DUT is short for device under test. The test code drives values onto the input ports of the design being tested and monitors the outputs of the design also. And as noted, we use Verilog code for the test part and for modeling our design. The Verilog code for the testing part is only used during the simulation phase, where the correct functionality of the design is verified. The Verilog code for the design is also used as part of the simulation phase when checking the functionality of the design, but this code is also used by a separate process known as synthesis, in which the design code is actually translated into a connection of logic gates, which will become the real physical digital hardware. Let's see an example test bench. The test bench is a module defined using the module keyword with a module name that you specify using a valid identifier. In this case, the module name is testbench_and_r. For our test bench, there are no ports, so we omit the port list and we end the module heading with a semicolon. All modules end with the keyword end module, and we include that at this point. The purpose of the test bench is to test one or more designs. In this example, the test bench is used to test our earlier design called and/or. We need to specify what module we are testing, and that can be achieved with this line of code shown here. The name of the module that we want to test is specified, in our case and/or, and this refers to our previous definition for the module and/or. So this is where we've defined our module in terms of the interface via the port list and what the module actually does. So this is the module definition. In addition to specifying the name of the module we are using, we also specify an instance name. And in our example, it's an identifier that we create, and we've just called it A1. The next important part of using the module is to make connections to the ports for that module. And for our design, we have 3 inputs, A, B, and C, and we've 1 output. So we don't need this other connection here. And to make a connection to A, we specify .A, indicating that we're making a connection to port A, and we provide between the brackets a connection. So in our example here, we're connecting in1 to A, and that's shown with this section of code. Likewise, to make a connection to the B input, we do so with this section of code here. So what we've got is a comma separated list. So you can see we've commas separating each connection, and to make a connection we specify the name of the port coming from our module definition and the connection we want to make to it. In this case, in1, in2, in3 for our 3 inputs, and out1 for our output G. At this point, don't worry about the difference between reg and wire. We'll come to that at a later point. All you want to be aware of is that we make connections at this point. This line of code is an example of what's known as a module instantiation. And it's a very important idea when using modules in Verilog. It may look like calling a function in C or in Java, but it's important that we don't use the word function call or module call, because what actually happens is something very different when we perform our simulation. So with our module instantiation, we create an instance of the module and R, give it a name, A1 in this example, and make connections to the ports for that module. So at this point, this line of code with these declarations here allow us to instantiate our design module and make connections to the ports. The next step then is to establish the test code that provides values that we can drive onto the inputs and code that we can use to monitor the outputs. This block of code here is an example of the initial construct, which is used to provide input values at different points in time to our design module. The exact details of what's happening here we'll cover in a later lecture. At this stage, the important point to note is that it's a way in which we can provide different test values to the design that we are testing. And the last piece of code that's relevant is this block shown here, which uses an always construct. And the purpose of this is to monitor the output. In our case, we've only one output, so we don't need this connection here. And with our output, we want to see what that value is when we provide different test input values. And to do that, we can use what's called a strobe task, and that just displays output to an output window when the simulation runs. So again, without going into much detail, we note that this is a way in which we can monitor or observe the output of our design. The idea of module instantiation is important, and in the last slide, the and/or module is incorporated into the test bench by instantiating or creating an instance of that module, and connections to the ports are made as part of this instantiation. Instantiating a module allows a copy of that module to be incorporated into another. So in our example, the module and/or is instantiated in our test bench module, which effectively means that we're inserting a copy of the and/or module into the test bench. What we mean by a copy will become clear when we go through an example simulation run. Multiple instantiations of the same module can occur if needed, and again we'll see examples of this at a later stage. Each instantiated module results in its own copy being included in the module where the instantiation occurs. And each copy has its own unique name given by the instance name, which in our example is A1 for this particular instance of the module. Multiple instantiations typically occur inside design modules. And just to be clear, the purpose of the instantiation is to incorporate our design into the test bench. And that we do with this line of code here. And when you incorporate the design, we make connections to the respective ports as part of that instantiation process. We have a module definition in which we model a specific operation, and as part of this we define the input-output interface using a port list. And it's important to distinguish between the module definition, which for our example is shown here for the AND/OR, this is the module definition, and the module instance where we instantiate the module, and that's shown here. And this is an example of a module instantiation, whereas the module definition is given here.